When the walls around you start to move, how do you react? How do you want them to behave? And how do you communicate with them? In this research, we explore human-robot interaction in the context of cyber-physical architecture, specifically shape-changing walls. Our investigation has two parts: speculative design and empirical elicitation. Together, these studies show us something that might seem like a paradox. If we want to give users more control over these robotic environments, then we may have to let the environment infer things that the user did not explicitly command. Let's start with our design study. Study 1. What makes a shape-changing environment valuable? We invited 20 architects and designers to our lab, where they could see a prototype of our robotic wall. In a series of design workshops, they asked us questions, they shared their concerns, and they sketched their visions for what cyber-physical architecture could be. This led us to a spectrum of 11 values, which describe the desirable qualities of a shape-changing environment. Some have more to do with functionality, others have more to do with communication and the types of relationships a person might have with an interactive structure. In between, there are values that are sometimes in tension with each other, for example, between cognitive offloading and preserving human autonomy. This sets the stage for Study 2. How do users interact with a shape-changing environment? We conducted a Wizard of Oz elicitation study using our prototype robotic wall. We wanted to take a concrete task and find out what actions came most naturally to users. We gave our participants a series of cards showing colored squares in various positions. Each square represented a plastic block. The participants' task was to create shelves from the wall and place these plastic blocks at the same locations that they saw on the card. Once all the blocks had been placed, they had to retrieve them and return the wall to the flat state. Along the way, the wall would make small errors, such as deploying a shelf too high or too low. In these situations, participants would have to make adjustments. The study took place over 4 stages. In the first stage, users were allowed to interact with the wall in whichever way felt most natural to them. They were told that the wall could hear them, see them, and feel them. In the second and third stages, we restricted their interaction modalities, either only vocal actions like speech, or only physical actions like gesture or touch. In the final stage, they were once again free to act however they liked. But instead of choosing just one mode, the majority of users combined vocal and physical actions in the final stage. Interestingly, half of this group had started the study preferring only physical actions. But after discovering new techniques in the forced choice stages, they added voice commands to their repertoire. One way to visualize these voice commands is by creating semantic embeddings for each vocalization, and then plotting them in a 2-dimensional state space. And by assigning natural language descriptions to physical actions, we can do the same thing for gesture and touch as well. Examining a user's pattern across these state spaces allows us to get a sense of their interaction style. So, what do these 2 studies tell us about designing room-scale robotic interactions? There are several implications, but let's focus on one. We know from our design workshops that we want to preserve human autonomy, which means that a robotic wall should not overstep its boundaries, and it should be responsive to user commands. But in our elicitation study, we saw that many user commands are ambiguous if they're looked at in isolation. The specific meaning can depend on the user's previous actions, or the current state of the wall, or where the user is looking or pointing. Users could give all this context explicitly, but that's a larger cognitive burden. And we know from our design workshop that cognitive burdens are valuable to reduce. What this means is that we should not try to create a direct mapping of user commands to robotic responses. Instead, we should interpret user actions, the robotic state, and the surrounding environment as pieces of statistical evidence, which can shape a probabilistic model of evolving user intent. For details and additional findings, please see our paper.